Assalamualaikum and good day everyone. Today we're going to start our chapter 2, which is Euclidean vector spaces. We will have three things to cover in this chapter. We start with vectors in Rn, linear combinations, linear dependence and linear independence. All of this we will cover in week 3. For now we will start with vector in Rn. We define a vector with n entries as n by 1 matrix. Vectors are used not only in mathematics but in virtually every branch of science. In this chapter, we will study a set of vectors and analyze their additive properties. The concepts presented here in the context of vectors are fundamental to the study of linear algebra. N vector. If n is a positive integer, and n vector is an n tuple, we call it n tuple, u1, u2 until un, with each coordinate is a real number. So the set of n vectors is denoted as Rn. R2, here 2 consists of an ordered pair of xy, so we have 2. So in R3, we consist of 3 vectors in 3 spaces and continuously R3, R4, so we have, let's say for R2, we have 2 here, this is a row vector and this is the column vector. For R3, we add another one here, 1, 2, 4, and the column vector also become 1, 2, 4, 3. If 4, we add another one. This slide shows example of R2, R3, and R4. As you can see, R2 we have 2, R3 we have 3, R4 we will have 4, and so on. Vectors. Vectors are typically denoted with boldface, lowercase letter. In this case, it's represented by V here. When we've explicitly given the initial and terminal point, the start and the end, we will often represent the vector as, for this A, B, means that the start is A and then going to B. Two vectors with the same magnitude but different directions is different, and two vectors with the same direction but different magnitude also different. So you can see this is different because we have different direction. This vector is different because of the magnitude. Same direction, but the magnitude is different. Vectors with same direction and same magnitude are called equivalent. And even though they may have different initial and terminal points, we think of them as equal. So if V and U are two equivalent vectors, we will write V is equal to U. So equivalent vectors means that same direction and same magnitude. This one here, all same direction and same magnitude. So we call it equivalent. Geometrically, in R2 and R3, a vector is directed line segment from the origin to the point whose coordinates are equal to the components of the vector. For example, if you can see here, V12. You can say it is a directed line segment from the origin 0, 0 to the point 1, 2, where the x is 1 here. You can see the x factor is 1 and then the y-axis is 2. So, directed line segment from 0 to 1, 2. The 0 vector, meanwhile, denoted by 0, is a vector with no length. Means that the 0 vector in Rn is the n vector which is equal to 0. So there is no length. If V is a vector, then the negative of the vector, which is negative V, is defined to be the vector with the same length as V. So the length is the same, but opposite direction. You can see this is the start here. So if V is towards here, and then the negative V is the opposite of V, we call it negative V, but the length is the same. The length is the same. So the negative of V, let's say here V1, V2 and V3 is negative V, and you put all the negative towards the V. If AB and CD are the endpoint of vector u and v. So for vector u, it is AB. For vector v, it is CD. Then A plus C, B plus D will be the endpoint of u plus v. So we have u here, which the end is AB. So we can say this is A and this is B. And for v here, this is C and this is D. So u plus v is the plus between u plus v, these two. So it should be A plus C, this one A plus C, A plus C, and then for the B here, these two, B plus D. It will be equals to what is u plus v. Here is another example. You can see here we have v1, v2 and w1, w2. So in this figure over here, we can see that the plus of v1 and w1 and v2 and w2 will get you the answer of v plus w. So v1 here plus w1 and v2 plus w2. Okay, now we will look into scalar multiplication. The product of ku of a real number k by a vector u is obtained by multiplying the magnitude of u by k. So we got here our u, this is our starting point, 0, u. So u. So this one, if you can see, the same direction, k is more or equal to 0, same direction, the scalar is 3, the scalar is 3 multiplied by u. And if the opposite direction, with k less than 0, we have negative of course, so negative 2 multiplied by u. So this is our u, and this is the k if more than 0, which is 1, 2, 3, 4 over here, and then if it is opposite direction, we add negative to that. This is the scalar multiples example. So this is our v, which is this long here, this is v, right? And if it's negative 2, so 2 times v, but in opposite direction, right? Because it is negative. 3 times v, so 3 times v, let's say v. So 3 times v here in the positive direction. So it's over here. Half v is half of the v. So we have a v here. And then half of this b. As mentioned before, for addition, the resultant of u plus v of two vectors u and v is obtained by the parallelogram law. U plus v is a diagonal of the parallelogram formed by u and v. So we see in the previous example where we have u plus b here, so we already know that u and v, the end result is u plus b will be here, based from our previous example. Two n vectors are added by adding their respective components. For example, let u and v be vectors in Rn. So we have u, u1, u2 until un, and you have v, v1, v2 until vn. So if u plus b, the first one is u1 plus v1, and then u2 plus v2, and continuously until un plus vn. Same goes with addition of column vectors. If you can see here, if you have a vector like this in a column format, u1, v1, so for u plus v, u1 plus v1, u2, v2, for u plus b will be u2 plus v2 until un, vn, so un plus vn. Suppose that we have two vectors, v and w, so this is our v and this is our w. Then the difference of W from V, denoted by V minus W, is defined to be V minus W is actually equals to V plus negative W. So we know the negative equation of W, if you have negative equation, it should be the opposite, right? The opposite of W. So this is our negative W. So V plus negative W. So this is our parallel line here for V. This is our parallel line for negative W. So this is the line. So V minus W is equals to V plus negative W. N vector is multiplied by a scalar by multiplying each component by the scalar. For example, let U be a vector and K be a real number. So we have K real number, U a vector. So we must multiply by each of the component in U. So U1 K, U2 K until UN K. Same with the column here. If you have a column like this, whereby K is the real number and U is the vector, so K here will be multiplied by every component of U. So it becomes KU1, KU2 until KUN. Here we have a few examples of what we have learned today. So we try to see one by one. So let's say U, the vector U is 1, 4, 5, negative 3, and vector V is 8, 1, negative 2, negative 1. So if U plus V, as you know, 1, 8, 4, 1, 5, negative 2, negative 3, negative 1. Okay, this is how we should have done. 1, 8, 4, 1, 5, 2, negative 3, negative 1, because it is according to their places. For 2, you have scalar 2 here with U. So multiply by each inside the U. So we have 2, 1, 2, 4, 2, 5, and 2, negative 3. And we have scalar with the minus here. So we have scalar 2 and scalar 3, but 2 with U, 3 with V, negative 3 with V. So we do the same operation here, like 2U over here, and then we do operation for 3V. Then we will do the addition for each of the places. 2, negative 24, 8, negative 3, 10, 6, negative 6, 3. And then you will get your answer. So for any vectors U, V, W that belongs to Rn, and any scalars K1, K2 that belongs to R, we have to remember this theorem. So we have 1, 2, 3, 4, 5, 6, 7, 8. We need to remember and understand this theorem in order to solve problems regarding vectors. If V is a vector, then the magnitude of V is called the norm of the vector and denoted by this symbol. Furthermore, V is a vector in R2, then, so we have V here, the norm of the vector. If it's 2, so V1 plus V2. And V is in R3, we have 3, right? Remember, before this we have learned. So the norm, this symbol, so we have V1, V2, and V3 because of R3. Let U and V be vectors in Rn. So we have U here, which is U1 until UN, and we have V, which is V1 until Vn. So to know the distance between U and V in Rn is known as Euclidean distance and can be computed using the following formula. So you must remember the formula. So distance UV. is equals to this formula. So u1 minus v1 squared plus u2 minus v2 squared plus until un minus vn squared. Okay, the norm or length of vector u, let's see we have vector u here, is written like this, is defined to be non-negative square root of u. So this is our equation. But we can observe that the distance of uv actually is equals to the norm of u minus v. We can see this here based from our equation of distance uv, where you have u1 minus v1 squared. So if u here, if u minus v here, the norm, it will be u1 minus v1 squared plus, right, u2 minus v2, oops, sorry, v2 squared plus u3 minus v3 squared, and so on. This is where the norm of the vector is calculated, or the length. So we can see this equation that you calculate here will be the length of this v1, v2. Let's look at this example where we have two vectors u and v. So vector u we have 1, negative 2, 4, 1, and for vector v we have 3, 1, negative 5, 0. To calculate the distance of u, v, so we need to use this equation where the u1, v1, u2, v2, u3, v3, u4, v4. We minus it and square. So we get your answer. To find the norm of v only, so we just insert the v squared. So v1 squared, v2 squared, v3 squared, and v4 squared. Then you will get your answer. Here we see another example. So we have two vector u and v, and find the distance between u and v in R4. So, and the distance is u minus v, the norm u minus the norm v, right? Because it is the same. So actually, this is for u1 v1, u2 v2, u3 v3, u4 v4. Then you calculate and you will get your answer. Now we're going to discuss about dot product and cross product. These two products are special products of vectors. The dot product is sometimes called the scalar product or the Euclidean inner product. If u and v are non-zero vectors in R2 or 3, and if the angle is the angle between this u and v, then dot product of u and v can be denoted as u dot v here, and defined as u dot v, the length of u, the length of v, and the cosine of the angle. If u and v equal to 0, then we can define u dot v to be 0. The examples show us on how to find the dot product for the following pairs of vectors. So they give us vector u and vector v, and the angle is 45 degrees. So we calculate the magnitude or length of u and length of v. Then for the dot product, we use the calculation, the equation that have been given, and you will get your answer, which is 6. Another example, we have again two vectors u, v, and the angle is 90. So you calculate the magnitude of u, the length or magnitude of v. Then we use the equation where we will get our answer, which is 0. Okay, how to get the correct angles? If the angles between two vectors are not given or known, we cannot compute the dot product. For computation purposes, it's desirable to have a formula that can express the product of two vectors. Okay. This slide shows the dot product of n vectors. So we let u and v vectors in Rn. So we have u and v as vectors. The dot product of u and v denoted as u dot v, and it can be represented in u1 v1 plus u2 v2 until un vn. This slide shows vector u and vector v in 3 spaces and 2 spaces, where if we have 3 spaces, we have u1 v1 plus u2 v2 and u3 v3, and for 2 spaces only u1 v1 and u2 v2. Now we have come to cross product. Cross product is different from dot products. Cross product gives us new vectors, but dot products that we have just learned give us a scalar. Here we have two vectors u and v in 3 spaces, and the cross product can be defined in 3 ways. The first one using vector notation. Using vector notation, for the first one here, it is without u1 and v1. Okay, and then the second one here without u2 v2, and the third one here is without u3 v3. The second way is using 2 by 2 determinants. As you can see, the same as previous one. This one is without u1 v1. The second one is without u2 v2. The third one is without u3 v3. So we already learned how to calculate this before. This one multiplied by this, and then minus the multiplication of this. The third way is by using a 3 by 3 determinants. So we represent I for u1 v1, j for u2 v2, k for u3 v3. And then for this I is without u1 v1, j is without u2 v2, and k multiply with the one that without u3 v3. This example asks us to compute the cross product for vector u and vector v. So this one using the third way, using a 3 by 3 determinants. So the cross product for u and v presented by I, j, and k here for each v1, v2, v3, u1, u2, and u3. So this is without u1, v1. This is without u2, v2. This is without u3, v3. This is without u3, v3. Okay, then you can get the answer here. So replace the I here because I is 1 here, then other one with 0, and then the second one, the j is 1, and then for the third one, the k is 1. Then you will get your answer, negative 61, negative 25, and 19. Write this example, ask you to compute the cross product u and v. The cross product here using the second way, using 2 by 2 determinants. So if you do AD minus BC here for each of these matrices, then you will get your answer 2, negative 7, and negative 6. Linear combination. Alright, here we are given S equals to V1, V2 until Vn, set of vectors in Rm, and let C, C1, C2, and Cn be scalars. So an expression of the form V is equal to the scalar and the S. So C1 V1 C2, V2 until Cn, Vn. This is called as a linear combination of vector S. Okay, for example, consider a set of vectors. We have 2, V1 and V2. Can it express the following vectors, U and V, as a linear combination of V1 and V2? In order to say the first vector U, which is this one, the vector U, to be linear combination of V1 and V2, we must have C1. This is our U1, our V1, sorry, this is our V1. And V2 multiplied by the scalar C1 and C2. And you will get this linear system, which is the V1, V2, and this is our scalar, and our U. Then change the linear system to augmented matrix. Okay. Then find the C1 and C2. Alright. Then we make the row operations. Then we have just learned in our chapter 1. Alright, and we get our echelon form. Then we can find our C1 and C2, which is C2 is 2, and then C1 is -3. Then we replace the C1 and C2 with -3 and 2. In order to find the second vector W to be a linear combination of V1, V2, we repeat the same process that we have done towards vector U before. So we change to the linear system, and we must find the C1 and C2. Then we change to augmented matrix and do our row operations. But for this one, we still have value on the third row, but we only have C1 and C2. So we decided W cannot be expressed as a linear combination of V1 and V2. Another example here asks us to show that the matrix A is a linear combination of these matrices M1, M2, and M3. First, we must find the values of C1, C2, and C3, same as the previous example. So we have C1 with M1 plus C2 with M2 plus C3 with M3, that will equal to our A's. Alright, this is our C1, this is our M1, this is our M2, this is our M3. Then we perform the scalar multiplications and additions, so we will get this equation. Then we can make this equation into this form. So solve these equations and you will get your C1 and C2 equals to -1, C3 equals to 2. Thus, matrix A is a linear combination of matrices M1, M2, and M3. What is linear dependence? So we consider a set of n vectors, v1 until vn, which have the same length of m. They are said to be linearly dependent if there exist n scalars when you solve the equation. Thus, we require at least one of them to be non-zero. If, say, C1 not equal to 0, then we can write this equation where it can be divided by C1. Before this, we say that for linear dependence, we need one of them at least to be non-zero. And if all of them are 0, which is a trivial solution, we can say it is a linearly independent. There are three properties of linearly independent sets. First, the empty set is called as linearly independent. A set with a single non-zero vector also a linearly independent, and a set is linear independent when the only representation of 0 as a linear combination of its vector are trivial. Consider the following equations where it is a homogeneous system and it has a trivial solution. If the trivial solution is the only solution, then the given vectors are linearly independent. If there are non-trivial solutions, then the vectors are linearly dependent. Example 1. Determine whether the vectors v1, v2, v3 here are linearly independent or not. First, we make it into this form C1 v1 plus C2 v2 plus C3 v3, and then after that we change into the augmented metric form, and then we do the row operations until we get to the echelon form. Then we can see here our C3 is free and it is a non-linear variable. So we can say that C1 here is equal to negative 0.5 C3. C2 is also negative 0.5 C3. These are non-trivial solutions, hence they are linearly dependent. For example 2, they give us three vectors I, j and k, and then same as before we change to this format. Then we go to the augmented matrix, but in this case we already find out that C1 here is equal to 0, C2 here is equal to 0, C3 here is equal to 0. So we can see all of them solutions is 0. So it is a trivial solution. Thus, the set S here is linearly independent. For example 3, we have three vectors v1, v2 and v3, and they ask us to determine whether the above vectors are linearly independent or not. Solution is, again, we make into this form C1, C2 and C3 is equal to 0, and then we make the vectors into the system equation. Then when we change into the metric representation, we get this equation. So, solving this linear equation by metric operations, we found that C1, C2 and C3 is equals to 0. So all of them is equals to 0. This indicates that the system has the trivial solutions. So the trivial solutions is what we call as linearly independent.